Okay, so this idea that you can assign feature vectors to internal nodes of a tree all the way to a root, starting from the vertices of this graph. And this tree is constructed by a sequence of edge collapses, induces a type of neural networks that are called recursive neural networks. Now, I say recursive and I put a V in the abbreviation to distinguish them from recurrent neural networks, which are common in things like natural language processing or audio processing. And the difference is roughly as follows. Both of them process graphs after a fashion, but recursive neural networks or recurrent neural networks process chain structured data, in other words, linear sequences, and recursive neural networks process data that can be organized hierarchically, in other words, trees. Okay, so the idea behind a recursive neural network is exactly what you saw in the visualization of the previous slide. You repeatedly merge two nodes into one. Each node has an n-dimensional feature vector computed recursively, and this happens as follows. So you take this little, atomic unit happening in the tree, where a parent node P is formed by combining the children C1 and C2. So P has a feature vector, C1 and C2 have feature vectors of their own. And we'll use the same letters to represent these feature vectors. And then associated with this merge is a weight vector and a bias term to shift the result away or towards zero. And so the code associated with the parent is, as in the formula, the weight vector times the concatenation of the children's feature vectors plus the bias term passed through some sort of nonlinearity on each of its dimensions, which is this f, right? So that's like a sigmoid or a ReLU or some such function. Okay, so again, we've started with feature vectors for the children and derived the feature vector for the parent. We'll talk in a moment about where these initial feature vectors come from, but for now, let's assume that at the beginning, we had some set of numbers describing each node of this graph. Right? Now, as you do this bottom up, doing an edge collapse each time, you end up with a fixed n-dimensional vector for the root encoding the whole tree. So it's one single n-dimensional vector, n numbers, and it encodes the whole tree. And if you do things right, you can train another neural network that takes this n-dimensional vector and blows it back up, reversing the sequence of collapses into the original graph, or at least something pretty close to it, modulo cycles. Okay, so this sort of idea has been used for parsing natural language sentences. It's used briefly for parsing natural scenes with more or less success. And so what we wanted to see was, can we use this for processing structural representations of three-dimensional shapes? So let's look at how that might proceed. So we are going to try to encode the parts of a chair with this recursive neural net formalism. Right? Now, if you look closely, you might be able to make out that two parts in the chair are highlighted right at the bottom, the front right leg and the front left leg. Right? And the merge is basically going to collapse these two. And on the right, I'm going to track what happens to their feature vectors. So I take the codes of these two, x1 and x2. I'm going to pass them through this function that applies a weight vector, adds a bias, passes it through a nonlinearity, and produces the code for the parent. And these two parts were adjacent, which is why there was an edge between them in the source graph, and which is why we chose to merge them. Right? Now I noticed that the legs on the left and the legs on the right are symmetric counterparts of each other. So there's a reflective symmetry relationship between them. So I can represent this with another transformation of the feature vectors. I merged the left and the right into one group, and I do some sort of slightly different transformation to figure out the feature vector for this merged group. Okay, now I keep going, right? So there's another reflective symmetry between the rod on one side of the back and the rod on the other side, and I keep going. So I'm merging more and more, and the pink in the chairs and the roots of the subtrees is growing more and more. Those pink regions are growing bigger and bigger. Now at this level, I've got all of the bottom of the chair in the left group and all of the top of the chair in the right group, and finally all of it gets merged, and I have some code up here representing this entire sequence. So I started with the leaf codes here, and then I merged it through a sequence of mergers formed by collapsing the adjacency and symmetry relationships in this structural graph. Okay. Now, this is where things get interesting, right? So I have a way of taking a shape and collapsing it down into a single n-dimensional feature vector. That's what I'm going to call a recursive encoder, RVNN encoder. And now I'm going to construct a decoder that's going to take this n-dimensional vector and then blow it back up into a tree whose leaves will represent the parts that I wanted in the first place. Right? And once I reconstruct these leaf nodes, I can try to correlate them with the parts that I started with, measure the error, computer loss, backpropagate it to train each part of this network. Now, the one thing I should mention, and I forgot to mention, was that the merge operation at every level is determined by exactly the same neural network. The same weights are applied for the merge operation, regardless of whether you're merging two legs into one or the top of the chair and the bottom of the chair. So a very high level merge and a very low level merge use exactly the same weights and bias and nonlinearity. That's why it's called recursive, because you are recursively stacking the same function on top of itself at every level of the tree. It's still a deep neural network because you have this compositional structure, but actually it has far fewer parameters than common neural networks, because you're not just sharing the weights at throughout a layer, but you're sharing them all the way up and down the tree as well. Right? So there's just essentially one or two small kernels to learn. And so this is the autoencoder version of a recursive network. You encode a shape into an n-dimensional feature vector and you decode it. But this by itself is probably not enough. The nice thing is now we have this way of representing each shape in regardless of how many parts it started out with in this n-dimensional space. This is unlike images where you essentially need an image input of the same dimension and it will get mapped to a latent vector of a certain dimension. Here you can take an arbitrarily complex graph and map it to the same n-dimensional space and reconstruct it back from this representation if everything goes right. I'm going to skip over some details here which are not super relevant at this high level, but from the autoencoder, remember when we talked about variational autoencoders, we said that we can take a standard autoencoder which is not generative, and then we can instead force its encoder to produce not a single code but its small Gaussian distribution over codes, which represents slight variations of the codes that could represent that same model. Okay. So we're going to do exactly the same thing here. We are going to take the shape coming in on the left, going through this recursive graph encoder. It produces a mean and a variance. We sample a latent vector from that little distribution, pass it into the decoder, and then try to reconstruct the chair. I'm going to show that visualization again, which we saw earlier in the discussion on VAs as well. We take different chairs, we encode them to different little Gaussian distributions, and we force all these little Gaussian distributions to mix and give you the standard Gaussian. So now if I want to sample new structural graphs, I sample an n-dimensional vector from this n-dimensional standard Gaussian all the way over on the right here. And then I pass it into my decoder. The decoder will derive a tree from this from this n-dimensional code, and that tree can be interpreted as a structural graph. Okay. I left out some bits that said that how you go from the final feature vectors attached to the leaves of this tree to an actual shape. There is a separate little network that interprets these feature vectors as defining the bounding box geometry of a part, but sort of we'll skip over those details for simplicity. It turns out that this by itself is not enough to get like really nice generation of structures. So it turned out that we had to add certain adversarial losses. So you got a VA and a GAN in one structure. Yes, it is possible to do this. We are not the first to have done it. There's prior literature on VAE GANs. But when you put all of this together, you get an encoder giving you distributions in a latent space, which are sampled, passed into a decoder, which is the G function in the middle, and then that gets judged by a discriminator of this adversarial network, and that bit is trained adversarially. Okay, so these sorts of recursive encodings of structural graphs turn out to be powerful for a variety of different applications in a high-level geometric structure synthesis. So we can do things like shape interpolation or synthesis. In this example, the chair on the left in green is interpolated to the chair on the right in red, and you can see that the intermediates in gray in the middle show topological changes as you go from left to right. So you start with 3 spokes in the wheel, then you get 4 spokes in the wheel, 5 spokes, and so on. But all you're doing to obtain this is just linear interpolation in latent space. And so I should have mentioned how you generate such an interpolation sequence. You take the starting shape and the ending shape, you process them through your encoder to get their latent codes, and then and these are both n-dimensional vectors, and then you just do linear interpolation between these n-dimensional vectors. You generate, let's say, 10 intermediate shapes, 10 intermediate codes, and then you decode each one of those intermediate codes to whatever the decoder tells you they should give you. Right? And in this case, this is a graph decoder, so it decodes structural graphs, and so we can interpret those as shapes, and you get these gray shapes in the middle. Right? So simple interpolation in latent space corresponds to extremely complex topological interpolation in the output space of shape structures. So you see these cardinality changes in the legs or in the number of slats in the back. The armrests appear slowly and things like that. Right? You can also use these for scene synthesis, shape composition, and various other applications. So there's a lot of interesting stuff that you can do with these structural representations. Now, in this particular example, we looked at essentially just binary merges apart with some caveats. So if 2 things are adjacent, then you merge them into one and you compute the code of their parent. Now, there was a nice follow-up paper called StructureNet, which took this idea and then allowed somewhat more general merges where you could merge 3 things or 4 things or 5 things together. The paper has some other limitations which the earlier work didn't have, but as a result, they were able to do more general merges. But then you think, okay, now I have to merge 2 things, 3 things, 4 things, or any arbitrary number of things using the same module. So how do we do this? So what they did was that they defined this tiny little graph neural network that operates in this little neighborhood of 2, 3, 4, 5, or whatever it is, using the methods that we discussed just before we got to recursive nets. And they use that as a way to take the codes of the children and produce a code for the parent, regardless of how many children there are. So I'm going to spare you the details, but that's the basic idea. Okay, so again, StructureNet shows nice examples of topological interpolation as you go from, let's say, an input on the left to the input all the way over on the right. They showed examples where they could encode things like point clouds and images to the same space so that they could show an example of synthesizing shapes that lie between a point cloud input and an image input, even though none of them are in the structural representation that they actually synthesize. Okay, and you can see the structural graphs that is produced by this process right at the bottom, associated with each of the generated shapes. Okay, so summarizing, we talked about some ways to process the structural graphs of shapes in order to predict the high-level layouts of parts and the attributes associated with these parts. This is in contrast to the low-level generative methods that we saw earlier, or at least the generative methods for low-level representations that we saw earlier, where you're trying to generate a point cloud or a voxel grid or a polygon mesh or something like that, which is not to say that those earlier networks don't learn high-level information. They do, but they learn it implicitly, as opposed to these methods where you explicitly inject this structural factorization into the network and make it deal with it as a first-order citizen throughout. Okay, now these RVNNs, graph networks, mixtures of those two are powerful models of this sort of structural layout, but as of now, they don't really model fine-grained local geometry very well. So they handle the high-level structure, but they don't tell you what the individual parts look like super well. So there is a bunch of methods that have tried to overcome this idea. Typically, they try to mix some sort of high-level structure prediction with low-level geometry prediction in the same pipeline, right? So the paper on the left is from a very nice paper called, I think, I've forgotten what the full title of the paper is, but they define a network that is driven by beta distributions, which can synthesize shapes which have both structural variability and variability at the part level within the same structure. The paper on the right is, as far as I remember, SDMNet, which represents parts as deformed cuboids. It predicts a layout of cuboids and then deforms these cuboids to try to model detailed local geometry, and it does a pretty good job of it. Okay. So there are these methods that have tried to overcome this, but there is another way of working around this problem which does not try to solve both tasks in a single pipeline. And that class of approaches is what I'm going to call detailization or conditional detailization. And the idea is as follows. We're going to factor shape synthesis into generating a high-level structure or a coarse scaffold structure, followed by generation of high resolution detail that fleshes out this structure into something that looks more detailed. And here's an example, right? So here's this sort of coarse scaffold. This is a voxel grid, which represents some sort of blobby shape. And I give it an example of the sort of style that should be used to make it look more detailed. And a neural network model takes these two things as input and outputs a shape which has the gross appearance of the coarse scaffold, but the fine-grained appearance of this detail exemplar on top. Right? So we can give it a different detail exemplar and it gets stylized differently. We give it another one and again it gets stylized differently. We give it a different one. Remember, the coarse shapes, if you squint, all look the same, but the fine-grained detail is obviously different. Here's another one with a different example for what the detail should look like, and here's another one, and so on. Now, do note that the detail exemplars in their core structure do not look at all like the core scaffold at all. But somehow the high resolution detail is being factored out from the detail exemplars in green on top and being applied to this core structure to make it look like something which is much more high resolution and detail. Okay, so this class of methods is what I'm going to call detailization. I'm going to talk about two different types of detailization. So the first thing I'm going to talk about is, again, because I think this is interesting in the context of geometry processing, a particular type of detailization that is predicated on a very, very, very classical method. And this method is called mesh subdivision. Now, subdivision is a process that is standard for mesh refinement. It's used to define modeling primitives called subdivision surfaces. The general idea is as follows. We start with some very, very coarse polygon mesh, bottom left. And then we take each of its faces and using a fixed rule, we refine it into a smaller number of polygons, and we define exactly what the geometry of those polygons is going to be. Right? So you start with this, shape bounded by a few triangles, and then you subdivide each of its faces. So now each of those triangles gets split into 4 triangles, and you repeat this each time. Now, this particular subdivision rule is called loop subdivision. That's the rule you see in the 2 dashed boxes. So there is a topology update rule in loop subdivision which says that, which says that every triangle is split into 4 sub-triangles. That's what the topology of the resulting mesh looks like. And then there's a separate rule that says that every vertex in this subdivided mesh is now assigned a position which is a weighted sum of its neighbors, and the weights are given by some very particular values. Right? Now, the particular values that are chosen for classical schemes of mesh refinement essentially drive the limit surface of this process. Like if you keep on subdividing until you can't make out the triangles any longer, the limit of this process is designed to be extremely smooth. So if you take it all the way, in this case, you will essentially end up with a sphere or something very close to that. Right? And the problem is that if you are trying to subdivide a real world mesh in order to detailize it, in order to increase its resolution and imbue it with detail, then this is bad for high frequency features because everything gets blurred out into these smooth curves. This is great for modeling surfaces of cars when you know you want that sort of smooth result, but you don't always want it when you're trying to super resolve or upsample existing shapes. Okay, so the classical subdivision is bad for high frequency features. And let's say I give you this coarse shape, and that's the ground truth for what it should actually look like if you increased its vertex count. If you apply classical methods, then you get these not particularly great looking results. So midpoint subdivision doesn't even give you smooth results. The others give some specific type of results which are not like super plausible and have all sorts of artifacts. So it turns out that you can replace this little kernel that takes one triangle and divides it into 4 with something that is driven by a small neural network. So you took these fixed weights that were used to compute the positions of the new vertices, and you replaced that. So this is a geometry update rule, and you replaced that with a small neural network that tells you the position of the new vertices. It's a pretty small network. It doesn't need much training data. It can be trained on just one mesh, for example. And it still gives you much better results, the one in blue, than the ones obtained by any of the classical methods. Okay. All right. So I'm going to skip over a bunch of details because we don't have much time. I am going to actually the subdivision process involves recursion in the style of a graph neural network. So there's message passing along the edges in a small neighborhood of each vertex and each edge. But again, I'm going to sort of spare you the details. Right? But basically, this is a type of recursive neural network, except it's not operating on a structural graph. It's operating on a mesh graph and doing message passing in between. And you're increasing the resolution of the mesh each time by splitting each edge into 2. Right? And it turns out that you can super resolve meshes, like very, very coarse meshes, very effectively with this sort of mechanism. If I give you the gray coarse meshes on top, you can super resolve it to these fairly nice looking results in blue at the bottom. And this gets trained on exactly one training shape. So that one training shape, because all you're learning is a local operator, and again, this is a sort of vote in favor of implicit functions and completely local processing. These very local types of operators can be trained on extremely little data and still produce great results, because even though there is one shape, that shape has thousands or millions of local neighborhoods that you can train on. Okay. If you give it different types of training data, it will upsample in different ways. It will produce sharp edges if you train it on man-made shapes on the left. It will produce smooth results if you train it with smooth shapes on the right. But this only goes so far, right? So the network is too local to capture detail with more complicated structure like those plants that we saw in the original, in the first slide that we started with. Okay, so how can we make this better? How can we generate results like those plants? And it turns out that in this case, we can work with a naive representation like voxel grids, because that's still okay for the level of super resolution that we are trying to achieve. But we're going to, again, work completely at a patch level. We're going to work at the level of local patches, not just wandering neighborhoods of vertices and edges, a little bigger than that. But again, this is a patch-based network. So again, look at local patches. What does this look like? So you, again, I mean, how much time do we have? I'll probably skip over some of these details. Okay, so the broad idea is that all of these networks are trained with what are called self-supervision. You give it a set of shapes, it constructs coarse versions of them, and then figures out how to invert this process to go from the coarse shape back to the detailed shape. Right? So you're given this detailed shape top left, you derive one coarse shape from it by self-supervision. You take another coarse shape that you got from somewhere else, and then you define certain losses, and then you penalize the output based on whether the patches in the super resolved or detailized output resemble those in your detailed shape or not. right? So there are a variety of objectives that drive this training, but they all operate by and large at the patch level to say, okay, this local region of my super resolved coarse shape looks like some patch from your detailed shape, right? And thereby you can transfer detail between two shapes that have completely different coarse structure, because if you just concentrate on one patch, you are likely to find another patch that looks very similar in your exemplar to start with. Okay, so there are all manner of results that we can go from this. You can take the coarse chairs on the left, you can super resolve them or detailize them using the detail exemplars on top, and you can fill out the matrix. So each of the red coarse shapes on the left has been detailized using the style of the green detail exemplars on top. So rinse and repeat results from chairs, results on tables, airplanes, motorcycles, and so on. Okay, so I'm again not going to talk too much about these. The high-level takeaway is that if we want to generate local detail, we can train separate models that are fairly local, that can be trained on relatively less data, and that can ingest the input of generators that produce coarse shape representations and super resolve them by imbuing their local patches with detail. Right. So that's, I think, the high level takeaway of this line of work and this line of reason. Okay, so where can we go from here? I'm just going to spend the last 5 minutes talking about things that I think people are interested in these days in this line of geometric deep learning and shape generation and so on. So one is, of course, the handling of fine-grained detail. Our representations, by and large, don't really process very high resolution detail very well, despite whatever I talked about in the last few slides. If you look at detail in the context of the pores on somebody's skin, well, we don't have good models of those, at least in 3D, even though 2D images, a 2D image generation is already at the stage where they can generate like very, very, very high resolution, let's say facial detail or foliage detail and things like that. So 3D and other types of geometric shape processing have a long way to go to catch up with that level of quality, and maybe some of the things that have been developed in the 2D image processing world can be brought over to generate shapes with much higher resolution in these different geometric representations. And I'm sure we'll see more like impactful work on that in the very near future. The other thing we'd like to be able to do is to condition these generators on various types of inputs. So we'd like to be able to type in a sentence saying, I want a teapot that is tall and has a spout that is shaped like a Q or something, or a J. And it should be able to give me the corresponding teapot, or at least something close to it. So this is the sort of thing that is demoed with image generation methods like DALL-E, for better or for worse. And I'm not saying that text conditioning is necessarily the best conditioning, but different types of conditioning which is more friendly to human users would make 3D modeling a more accessible form of creation or content creation to many more people. We'd also like to have much richer representations. So we'd like to be able to both handle things like structural graphs, which are way more complex. Think of the structural graphs of proteins, for example, and how can we generate these structures for drug discovery or protein folding and so on. And this will require a lot of domain-specific work, domain-specific architectures, domain-specific languages for which can be induced for describing these classes of shapes and so on and so forth. We'd also like to simultaneously, and sort of goes counter to everything I've said before, make these systems easier to train. We'd like to be able to train with fewer annotations, with fewer examples, so that we can do few-shot generalization. Few-shot means training on a very few exemplars. Your training set is very small. And the way to make up for this is with pre-training on other data sets or using domain knowledge. So that's something that we'd like to do. And we'd like to have richer objectives. We'd like to be able to link geometric structure and shape modeling with physical materials, with fabrication constraints, with predicates like function, motion, language, and so on. Right? So there's a lot of interesting work that is actively happening in this space. This is all pretty cutting edge. Many of the explored systems are still sort of toy-like. but it's getting better, and we'll hopefully be able to model like more real world predicates in these data-driven frameworks. So, okay, so I'm going to stop there, and I'm happy to take questions. Thank you so much for staying with me for an entire day. I know it's very tedious to hear one person for one whole day, but I'm happy to take any questions that you might have in the rest of the time.
So thanks, Sidharth. Before we have any questions, let's have a round of applause. I invite both the online and offline folks to. Okay, questions time. Folks have questions. Okay, there is at least one question, and we are waiting for the microphone to warm up.
Hello. Hi, Sidharth. So could you go back to the slide wherein you distinguished between the two kinds of convolution of graphs, the primal one and the spectral one?
Yep.
Like, could you explain once again how are we dealing with the issue that a particular vertex might not have the same number of neighbors as, say, some other vertex
in the left side case, right? The primal case. Yeah. I mean, yes. One way you could think about getting around this is to just okay. So imagine that you okay. So let's try. I'm going to try to think of a fanciful example that I can posit in terms of real example. So. Imagine that I live in a house and I want to figure out how much and I want to borrow water from my neighbors, right? So I may have 3 neighbors or 5 neighbors or 4 neighbors or whatever. So instead of borrowing it from all of them in one go, I can go to the first neighbor and say, okay, can you lend me some water? And they lend me, 1 liter of water. Then I go to the second neighbor and say, can you lend me some water? And they lend me 2 liters of water. The next one lends me, let's say, 3 liters of water. So over 3 neighbors, I have collected 6 liters of water, and I add it all up, and I have 6 liters of water. So I've applied exactly the same operation to each of the neighbors. I've queried them each for water, and they gave me different amounts, and I added it up. Right? So the approach here is essentially exactly the same. As a vertex, I look at all my neighboring vertices. I ask the first vertex, can you tell me your feature vector? That vertex says, yes, here is my feature vector, take it. I say, okay, I am going to multiply this feature vector, for example, by some weight vector W. So let's say the feature vector was x1. I say, so now I have wx1, and I store that wx1 with me. Then I go to the second neighboring vertex, and I say, can you tell me your feature vector? So this is, okay, here it is x2. I say, okay, you gave me x2. I'm going to multiply x2 by w, and then I'm going to store it within me. Right? And so I go around, and then I've collected wx1, wx2, wx3, and so on. And then I, let's say, add up all of them. Now, in this simple case, of course, it's just the multiplication distributes over the feature vector. So I get w dot x1 plus x2 plus x3. But you can think of this w function as something a bit more complicated, which doesn't distribute in that fashion. So I essentially end up with some function, some fixed function of x1 plus some fixed function, that same fixed function of x2 plus that same fixed function of x3, and so on. So I end up with fx1 plus fx2 plus fx3. Right? If I instead had 5 neighbors, I would get fx1 plus fx2 plus fx3 plus fx4 plus fx5. Maybe I divide by 5 to normalize this result, maybe. But I've queried each of these neighbors independently, and when I add them up, I get this result. So this operation, this function f, stays fixed regardless of how many neighbors I have, because I'm only applying it pairwise in every instance, and then just adding them by, let's say, simple addition. Does that make sense?
Yeah, it does. So I was thinking about relating how are we trying to relate it to the spatial convolution picture in cases of images or any other Euclidean domain. So in those situations, The convolution output at a particular point depends on the same number of neighbors.
Mhm.
Like if we have a 3 cross 3 kernel, then it
Yeah.
depends on 9 points basically.
Yeah.
8 neighbors and the vertex, the point itself.
Yeah.
That is not going to be the case in message passing, right?
No, that is not going to be the case in message passing. And I mean, one way of thinking about it is just to think that it is like image convolution, but where the convolution kernel has exactly the same scalar value in every cell of the 3 by 3 grid. You are going to treat every neighboring pixel exactly the same, right? Which, I mean, doesn't really make sense if that's all you did. But the nice thing is that first of all, you can get the response from many different kernels with many different weights. Plus, this function f need not be a simple multiplication by a weight. It can be something a bit more complicated, or it can be weighted by some other things like attention, etc., etc. So all you're doing is some sort of degree and permutation invariant aggregation over your neighbors. Does it translate to a classical convolution operation? Possibly not. I mean, maybe I should put convolution in quotes here. It's basically message passing and aggregation.
That was my next question. Like,
Yeah.
what sense do we call an operation to be a convolution operation?
Yeah, that's a great question. I think I should probably put convolution in big quotes on this slide. I mean, it's pseudo convolution where you're trying to mimic the idea of a convolution kernel over arbitrary local topologies.
Yeah, and I had a similar question with regards to the two kinds of convolution you defined for meshes.
Mhm.
One I think was the spatial picture, the other one was the spectral.
Right.
So is it just to confirm? Is it the case that the spatial picture is essentially the inverse Fourier transform of the spectral mesh convolution?
This.
Like if we perform mesh
Yeah. So because of the way the discretization happens, I mean, if you defined it in, analytically with like actual continuous functions, yes, I mean they are equivalent, assuming you use the same basis, etc., etc. But once you do this discretization in this fashion, I don't think it's exactly the same.
And my final question is that, like, in geometric deep learning literature, like I was having this discussion with Kaushik during the break, that in the deep learning literature, there is a lot of focus on building new kinds of convolution for different the manifolds.
Yeah.
Like, why are we so fixated about like creating convolutions for different kinds of manifolds? Like in some cases, the convolution might not even be so natural. Like considering the case of graphs, the convolution in itself isn't defined, but one defines it using the spectral convolution property. Like we multiply Fourier representation of two graph signals and then take the inverse Fourier transform and we claim that this is the convolution.
Yeah.
Rather than the natural case which happens in Euclidean.
Yeah.
So what's the reason that everyone is so excited about convolution, creating convolution?
Yeah, this is a really nice question. So I guess this also relates back to the previous question, about why, like what is it correct to call that sort of message passing based operation actually convolution? How does it relate to graph convolution, right? I mean, convolution in terms of the eigenfunctions of the graph Laplacian is actually, a way of defining convolution directly, but message passing is really a sort of bastardization of the idea of real convolution, whatever it is, and does not necessarily, it's not necessarily the dual of the spectral definition. I can't speak. I have not really spent much time on this sort of problem, so I can't speak for the motivations of the many papers that do exist in this space. Affine invariant to convolutions and so on and so forth. I think there are a few attractions. One is probably just the remarkable success of convolutional neural nets on images. I mean, maybe the idea is that if only we can get the convolutions right and invariant to the right class of transformations, then that representation will just be the best way to process meshes. Actually, technically, I shouldn't say that I never tried to do something similar. We tried to do this in almost exactly what you see on the screen here a long, long time ago. And basically, we got stuck. And then we gave it up and said, okay, what happens if we just render the local neighborhood and process that through some 2D network? And that turned out to work very well. Those are the view-based networks I talked about earlier, where you're essentially lifting the local space onto something like a tangent plane, but you're doing it by a rendering projection, a viewing projection, not by an exponential map or something like that. And it turns out that you can just process that, and that makes sense. So I think the incentive is, again, the wild success of convolutions for 2D images. And now you're probably going to see efforts to derive various types of ways of defining, let's say, transformers or diffusion models on 3D representations, because that's been so wildly successful in other domains. Also, I mean, defining convolution in nice ways on discretized manifolds is mathematically very elegant. I mean, there are all sorts of nice solutions for this. It's just that, does it translate to practically very useful methods? I think the jury's still out on that one.
Thank you. All right, yeah. So those questions were from Nilay, who actually works for Adobe here in Noida. So
hi.
Great. So more questions from folks in the room or online. Are there any more things to talk about? If not, I suppose it's been a long day for Sidhdharth as well, in addition to us. So it's been it's like the 8th day of the summer school. So we will maybe then break now, because we are like, I think we are probably saturated, and we have had like a great overview of graph neural networks in the context of shape modeling from you, Sidhdharth. But perhaps human limits are only so much. So thank you once again. Let's give him another round of applause and say thank you.
Thank you so much. I'm surprised that I'm really touched that all of you stayed with me for this long. I don't know how many people have dropped out silently, but yeah, all of you must be very exhausted. The organizers must be exhausted as well. So I thank you all for your patience. And yeah, thanks for having me.
Thanks, Sidhdharth, and hopefully catch you in person some other time. But
yep.
For the summer school, we'll contact you for some closure things. Yeah, and
sounds great.
Yeah, thank you. Great. Thanks everyone. Thank you.
Bye.